Welcome everybody to our next video on probability. Today we'll be talking about conditional probability. And what conditional probability is, it's the probability that one event will occur knowing that, or given that, a second event has already occurred. And some of the notation that we use to represent conditional probability would be probability, we have our prob notation, then inside the parentheses we have a vertical line, and then B. So what we use the vertical bar for is to denote that this is conditional probability. And we would actually read this as the probability of A given B. So that vertical line is there to kind of stand in for the word given. So what the probability of A given B actually is the probability of A and B, so the probability of both events occurring at the same time, divided by the probability of B. Another way of seeing that is that the numerator just becomes the number of ways in which A and B can both occur, and the denominator is the number of ways in which B occurs. Now, sometimes you might see this formula rearranged and looking something like the probability of A and B occurring is equal to the probability of A given B times the probability of B. So let's look at an example where this really comes into play. And what we're going to do is drawing balls from an urn without replacement. And so when you see these two words come up, without replacement, it really is exactly what it sounds like. You're drawing a ball, but you're not putting it back after you've drawn it. So the without replacement, once you take the ball out, or once you draw the card, or whatever it is, that is disregarded, and so it doesn't go back into the original object or urn. So suppose that we've got an urn that contains 3 red balls and 2 blue balls. And what we're going to do is to draw 2 balls out of this urn without replacement. Now, where the conditional probability comes into play, we can see that the second draw, the color of the ball that we get on the second draw, is really going to be dependent on the color of the ball that we drew the first time. Since we're not putting the ball back, once it's gone, the probabilities on the second draw are going to change. And so kind of picturing what's going on there, we've got originally 3 red balls and 2 blue balls. Well, if we happen to draw a red ball on the first draw, then we've got 2 reds and 2 blues. If we happen to draw a blue ball on the first draw, then we still have our original 3 red balls, but we're only down to 1 blue ball in that case. And so if we draw a red ball, the probability of drawing red, given that we've already drawn 1 red, is going to be 2 out of 4. The probability of drawing a blue, given that we've already drawn a red, is also 2 out of 4. But if we look at the other situation, where if we look at the probability of red given that we've drawn a blue, well, that's 3/4. And the probability that we'll draw a blue, given that we've already drawn a blue, is only 1/4. And so the probabilities are going to be different depending on the value that happened for our first draw. Probably the best way to visualize this is with something called a tree diagram. Now, we call it a tree diagram or a tree graph. Kind of the way that we'll draw it, it looks more like a root system for a tree than it does maybe the actual tree. And so at the very top, you've got something called the root node, and that's kind of the 0th level. And then the very first level, or from the root node, you're going to branch off into the possibilities that can happen, maybe say on the first draw. So on the first draw, we can either draw a red ball or we can draw a blue ball. And then from each one of those what those are called are nodes. So from each one of those nodes, we then branch again for our possibilities for the second draw. So if we draw a red ball, then we can branch again, and for the second draw, we can either draw a red one or a blue one. If we drew a blue ball for the first draw, then that node will branch into two other nodes, a red node and a blue node. And what we'll do is then label the probabilities, so we're going to have these labels on each one of the branches. Now those will be our conditional probabilities. So something that we'll talk about for these trees is something called a path. So a path through the tree is going to start at the very root node at the very top and go through go down to a node, and then from there follow another branching node and following another branching node all the way to the bottom. And so a path in the tree starts at the very root and goes all the way down to the very bottom. So what those probabilities are that are just above a particular node is those are going to be the conditional probability of passing through that node. And so on the first branch, branching from the root node, it's going to be, well, what's the probability of A happening? What's the probability of B happening on the very first draw? For the next one, it's a conditional probability. So from A down to A, that's going to be the probability of A happening given that A has already happened the first time. The branching from A down to B, that will be the probability that B happens given that we are already standing on node A, so given that A has happened. For the branch from B down to A, that gets labeled with the probability of A given that B has happened. And then finally, the branch from B down to B is the probability that B happens given that B has already happened. And so what you're seeing from an even bigger picture, so if we add on another layer here, well, from our root node, we branch to possibility A or possibility B. Each one of those branches to A's or B's. And for the third level, each one of those nodes branches to A or B. And so by the time you get to the very bottom level, suppose we've gone from the root down to A, down to B, down to A, then the probability for that last leg from B down to A is going to be the conditional probability of getting A, given that we've already passed through node A and then node B. So we have two nodes that we're passing through there. Likewise, if we go down through the path B, A, B, then the path at the very bottom, that leg gets labeled as the probability of B given that we have passed through B at the very top and A then on the next level. And so that's how we're labeling these conditional probabilities through the tree. So the probability of any particular path through the tree is going to be the product of the probabilities along each path. And so from the example that we talked about before, we had 3 red balls and 2 blue balls. Well, from the root node on our first draw, the probability of getting a red node or a red ball is just going to be 3/5, 3 out of 5. The probability of getting a blue is just going to be 2 out of 5. From there, if we continue to branch, so suppose that we had a red ball on the first one, well, now one of our red balls is gone, and so we're down to 2 red balls out of a total of 4. So we've got 2 red balls and our original 2 blue balls. So the probability along that node, along that leg, is just going to be 2/4. The probability from the red node, from the red to the blue, from the first level to the second, is also going to be 2/4. Now, had we drawn a blue ball on the first one, we still have our original 3 red balls, so the probability of drawing a red one after we've drawn a blue one is going to be 3/4. And the probability of drawing another blue one after we've already drawn one blue one is going to be 1/4. And so if we just look at the probability then of first drawing blue and then drawing red, well, that's going to be the product of 2/5 times 3/4 for that particular path. If we look at the probability of drawing two blues, then that takes us along the path from blue to blue. So that's going to be the product of 2/5 times 1/4 to give us 2/20. Now, some more complicated events may actually contain multiple paths. And if we have multiple paths in the tree, then we're going to take the sum of the probabilities for each path. And so, for example, if somebody was interested in the event where we draw one ball of each color, well, that's going to correspond to two separate paths. The path where we first draw red, then we draw blue, and it's going to also include the path where first we draw blue, and then we draw red. And so how would we compute that probability? Well, from our label tree, we've got the probability of one of each color is going to be equal to the probability of red then blue plus the probability of blue then red, because those are our two paths that correspond to the condition of one of each color. Well, for the path red-blue, we've got 3/5 times 2/4. For the probability of blue then red, we've got 2/5 times 3/4. So 3/5 times 2/4 plus 2/5 times 3/4 gives us 6/20 plus 6/20 or 12/20. So now if we look at an event where a single card is drawn from a standard deck of 52 cards. So what we're interested in now is the conditional probability of that we have a face card given that the card is red. So maybe we just barely catch a glimpse of the card and we see that the color is going to be red. So what's the probability that it's a face card given that information? Well, for the numerator, we've got the number of red face cards. For the denominator, we've just got the number of red cards. So the number of red face cards, we've got 6. For the total number of red cards, we've got 13 hearts, 13 diamonds, so we've got a total of 26. So that conditional probability is going to be 6/26. So maybe in another example, we draw 2 cards without replacement from a standard deck of 52 cards. So what we're interested in here is the probability that the second card is a heart, given that we know that the first card is a heart. And so for that one, kind of the easy way of thinking about that is just, well, we've drawn one heart, so how many hearts do we have left to choose? Well, there's only 12 of them. That's going to be our numerator. And so what about the denominator? Well, we started with 52 cards. We've drawn 1, so it means we've got 51 other possibilities left. And so that conditional probability is just 12/51. Now, this is kind of the intuitive way of doing it because the definition for doing it is a little more complicated. So if we were using the definition, what this would be is the probability of 2 hearts divided by the probability that we have 1 heart. And so the probability that we draw 2 hearts is going to be 13 choose 2 divided by 52 choose 2. Now the 13 choose 2, how many ways can we choose 2 cards from the 13 hearts that we have? The 52 choose 2 is just how many ways can we choose 2 cards from 52. For the denominator, what's the probability of drawing a heart? Well, 13 choose 1 divided by 52 choose 1, or just 13/52. And so when we look at 78, so 13 choose 2 is our 78. 52 choose 2 is 1,326. divided by 13 over 52. Well, dividing by a fraction, we multiply by the reciprocal. So this gives us 78 over 1326 times 52 over 13. Now, when we multiply those fractions and simplify them, it comes down to 4/17. And if we think back to the last answer that we did, we said, well, that probability was going to be 12 over 51. Well, 12 becomes 3 times 4. 51 is 3 times 17. So if we cancel a factor of 3, numerator and denominator, we end up with exactly the same answer of 4/17. So one way that another application that we can do for this is to say that we want to predict the weather. And suppose that we decide we can predict the weather in the following way. We say that the probability that it's going to be clear tomorrow, given that it is raining today, is just going to be a probability of 0.2. The probability that it will rain tomorrow, given that it is raining today, has a probability of 0.8. The probability that it will be clear tomorrow, given that it's clear today, is going to be 0.7. And the probability that it will rain tomorrow, given that it is clear today, has a probability of 0.3. Now, in addition to this information, suppose that we just happen to know that there's a 40% chance of rain on Monday, or there's a 40% chance that Monday is going to be a clear day. Then we can ask the question, what is the probability that it will rain exactly one of the 3 days, Monday, Tuesday, or Wednesday? Well, if we look at the tree diagram that kind of corresponds to this possibility, we've got two possible outcomes. We either got R for raining or C for being clear. So on Monday, it will either rain or it will be clear. For the next from each one of those nodes, we branch into two possibilities, either rain or clear for Tuesday. And for each of the Tuesday nodes, we branch into two other nodes, and it will be either raining or clear on Wednesday. So from the root node, the probability that it will be raining is going to be 0.6, and the probability that it will be clear, we already know that one, is going to be 0.4. From there, now we use the conditional probabilities that we kind of guessed at the very beginning of our problem. The probability of raining tomorrow, given that it's raining today, is going to be 0.8. Probability that it's clear tomorrow, given that it's raining today, is going to be 0.2. The probability that it's raining tomorrow, given that it's clear today, is 0.3. And then the probability that it's clear tomorrow, given that it's clear today, was 0.7. And so that gives us our conditional probabilities for the second branch. And then for the third branch, we use the same probabilities. We use the same conditional probabilities. If we see the step from R to R, that gives us a probability of 0.8. A step from R to C gives us 0.2. A step from C to R gives us 0.3, and a step from C to C gives us 0.7. And so our probability that it rains exactly one day on either Monday, Tuesday, or Wednesday actually corresponds to 3 different paths in our tree. It corresponds to the path RCC, it corresponds to the path CRC, and we have the path CCR. And so if we look at the probability that it will rain exactly one day, that's going to be the sum of the probabilities along those paths. The probability along a path is just the product of the numbers along the path. So we've got 0.6 times 0.2 times 0.7 for the path RCC. We've got 0.4 times 0.3 times 0.2 for the path CRC. And then we've got 0.4 times 0.7 times 0.3 for the path CCR. So that gives us 0.084 plus 0.024 plus 0.084 for our three paths. Adding those together gives us a probability that it will rain exactly one day of the Monday, Tuesday, Wednesday will be 0.192. So just shy of a 20% chance that we will have rain for exactly one day during those 3 days. So I hope this has been a good introduction to conditional probability, and in particular to trees, for how we tend to think about conditional probability and how things kind of branch and how things change as conditions change in our experiments. So I hope you've enjoyed it, and I hope I will see you guys next time.